In Chapter 9, we look at how the Black-Scholes formula and call and put prices are affected if we change some of the input variables, and we call these the Greek letters of the Black-Scholes formula. And then in the second part of Chapter 9, we particularly going to focus on the volatility of an underlying asset. We're going to show that this volatility is actually changing through time in the data, and then we talk about how we can adjust the Black-Scholes formula to take this time variation in volatility into account. So if you think about hedging using options, well then this hedging actually arises naturally from our derivation of put and call prices. If you think back to our binomial tree and to the first method how we priced option, we said that we buy some delta numbers of stocks and B numbers of bonds to replicate the payoff of an option, and therefore that value or that cost of building that portfolio pin down exactly that option price at the initial point in time. Now, if you think about if you want to hedge risks in an underlying asset, then what do you do? Well, given that you know that delta numbers of stocks and B numbers of bonds replicate the option, then you can just invert that equation, and minus 1 over delta numbers of options should perfectly hedge the risks in an underlying asset. To illustrate that, let's write down again what was this equation. We said an option price will be equal to delta numbers of stocks plus B numbers of bonds. And now if I want to invert this, I just bring S and the option price on the same side of the equation and set that equal to the bond price, which then basically says, look, I replicate the risk-free asset. Then the next thing which I want to do, I divide by delta. If you have one unit, one long position in the stock price, and I combine that with minus 1 divided by delta units of the option price, then I construct something which is the same as a risk-free asset. So in that sense, 1 unit of the stock can be hedged or remove all risks by taking minus 1 over delta positions in the option. So that gives me a risk-free asset position. Now, of course, we may also want to hedge other risks, not just movements in the price of the underlying asset, but maybe also what happens if interest rates change, or for example, if the risk or the volatility of an underlying asset changes. And we're going to talk about all these different possibilities in the next few slides. So we start with the option delta. The option delta captures how sensitive is the option price, or how much does the option price change as the price of the underlying changes a little bit. And so mathematically it's defined as taking the partial derivative of the option price, where the option price is some function of the price of the underlying, the volatility, interest rate, and time to maturity. We take the partial derivative of this thing with respect to that underlying price. Now for the call option, in particular for the Black-Scholes formula, we saw that the call price is equal to what you receive if you exercise that option, well, it's the underlying asset, times the probability that you actually exercise the option, that it's in the money. And that probability is taken under that artificial Q star probability measure, minus the present value of the strike price, so that's what you have to pay if you exercise the option, times the probability that the option is in the money, where now this probability is taken under that artificial risk-neutral probability measure Q. Now if you take the partial derivative with respect to S, the price of the underlying, it turns out that this is exactly equal to this probability of the option being in the money under that Q star probability measure. In some sense, you see that from this equation. Well, S shows up over here. Taking partial derivative leaves me just with that probability term. Now, it is a little bit more complicated because S also shows up within these threshold values D1 and D2, but it turns out when you do all the math that these terms actually disappear, that they cancel out. And you can do a similar thing for the put option. If you take the Black-Scholes formula for the put option, and you take the derivative with respect to S, then you get this is equal to this probability of that put option being in the money, and then we set a minus sign in front of it. That's because with the put option you have to deliver that underlying asset, and therefore the put option is negatively related to movements in the underlying asset price. For the call option, the delta is always positive and it's always between 0 and 1. And we can see that if you look at this following picture over here, that's a picture which you have seen in an earlier chapter, that blue, solid, and kind of checked line, that's the intrinsic value of the call option, while that red curved line, that's the price of the call option. The difference between the two is the time value of the option and the time value in the call option. We always know it's positive because you only have to pay the strike price in the future, and you have this cherry picking right where you decide whether you want to exercise the option or not. For the delta, what does it mean taking this first derivative? It basically looks at the slope of that red line, and depending on where you are on that red line, that slope might be 0 or it might be something positive, and the maximum we can take is exactly a value of 1. Now, what's the interpretation of this? Well, if you look first at this left-hand side, where the call option is deep out of the money, here you don't have any exposure to the price of the underlying, because basically you know for sure you're not going to be in the money, and therefore your option is not going to be exercised. And therefore, well, there's no reason to buy any stocks to replicate that option. On the other side, if you're very deep in the money, then you know for sure you're going to exercise that call, you know for sure you're going to pay strike price and you receive the underlying asset, and therefore to replicate now that option, you actually want to buy 1 unit of the underlying asset, which is illustrated by this delta equal to 1. What does this mean exactly? So if the price of the underlying further increases, since I know for sure I'm going to exercise, that means, well, the value of my option is going to increase even further. If the price of the underlying drops a little bit, it means that the value of my option is actually going to decrease. And that risk exposure is exactly 1 to 1 if you're very deep in the money. Anywhere in between, where you're not quite sure whether you're going to be in the money or not, whether you're going to buy the underlying asset or you don't buy the underlying asset, that's where the delta is going to be between 0 and 1. We can make a similar argument for the put option. Here the delta turns out to be always a negative number, and it's always going to be between -1 and 0. To make this argument, I want to look at that picture for the put option, where again we have this kind of blue solid checked line. That's the intrinsic value of the put option, and then this red line over here, this curved line, that's the price of a put option depending on where the underlying price is currently. Notice one thing, the time value of the put option can be negative. We have talked about that in an earlier chapter. That's when you're very deep in the money, you know for sure you're going to exercise that option. But again, with the put option, you actually only receive the strike price at the maturity, and therefore the time value of money works against you, and that time value of that option can be negative. Looking at the delta, if you're very deep in the money, so again here you know for sure you're going to exercise that option, meaning that you will receive strike price at the maturity and you will have to deliver that underlying asset. What does it mean I have to deliver the underlying asset? If the price of the underlying asset increases a little bit, that means I have to deliver something a little bit more expensive. It's bad news for me. If the price of the underlying asset drops further, it means I have to deliver something cheaper, which is good news to me. So in that sense, by me having to deliver the underlying asset, if I exercise that put option, that means I have a negative exposure to that stock price movement. So if you're very deep in the money, for sure you want to exercise that put option, you get a full negative exposure to this underlying asset price, and delta is exactly -1. On the other extreme, if you're very deep out of the money with that put option, then, well, it doesn't really matter how much the underlying price changes over here. I know for sure I'm never going to be in the money. To replicate that put option, I don't have to buy or sell any stocks at all. And so there's no exposure of the put option to changes in this underlying price, and therefore delta is 0. Anywhere in between, you don't know exactly whether you want to exercise that option or not, and so your risk exposure is somewhere between -1 and 0. So again, the delta in this picture is really just the slope of that red line at any of these points in time. So I illustrate that it varies from basically -1, then it gets closer and closer to 0 as the line flattens out. We have talked about this point already before. So we said that if you have a long position in the underlying asset, then just looking at this argument of the replication in the binomial tree of delta numbers of stocks, b numbers of bonds, if I actually have one long position in the underlying asset, I can hedge that by taking -1 over delta positions in either a call or a put option. Okay, so that followed this argument over here where I had this equation replicating portfolio is equal to the option. Well, I can rewrite that in terms of one long position in the stock -1 over delta positions in the option that replicates a risk-free investment. Now notice that for a call option, delta is always positive. That means you have -1 over something positive or a negative amount of call options. That means you actually have to short call options or sell call options to hedge a long position in the underlying asset. For a put option, the delta is a negative number. So you have -1 over a negative thing. So that means this term becomes positive. And so that means you actually have to take long positions or buy put options to hedge a long position in the underlying asset. As the price of the underlying changes, you actually always have to readjust your hedge of how many options you want to buy or sell, so for put or call options, to hedge a long position in the underlying asset. Why? Well, because our delta here for the call, depending on how high the underlying asset is, or for the put, depending on how high the underlying asset is, delta changes actually. So delta is sensitive to change in the underlying asset, and therefore your hedge has to be adjusted as the underlying asset changes its price. Notice another thing is that the delta hedge is only perfect in this Black-Scholes world, but it comes with many assumptions. Some of them are that interest rates are constant, volatility is constant. Of course, also in the Black-Scholes world, it means that the time steps in the tree becomes very tiny, and actually these up and down movements become also quite small. And so that delta, also from the point of view that it is a partial derivative of that option price, already suggests that it only captures how much the option price changes if the price in the underlying asset changes just a little bit. So if you now have larger changes in the underlying asset price, well then delta may not work anymore very well to hedge risks. And then we have to look actually at other Greek letters, and we see that in the next few slides. Some limiting properties of delta. For a call option, S going to infinity, that means you are very deep in the money. We have already seen that means that the delta of the call is going to be just 1. So 1 full risk exposure to the underlying asset. If S goes towards 0 or is 0, then the delta is going to be 0. That's the case where you're very deep out of the money. The call definitely is not going to be exercised in the future, and so the call price has no exposure to the underlying asset. And then we have some other limiting properties which are interesting to look at. What if you get very close to maturity, or what if there is basically no more volatility in that underlying asset? Well, then if the price of the underlying asset is actually larger than the discounted strike price, then you know for sure you're going to be ending up in the money. And so now we know that we need exactly 1 unit of the underlying asset to replicate that call option. And then if you just change the price of the underlying a little bit, and you change it such that it is less than this discounted strike price, or just out of the money, well then you know you're going to be out of the money for sure as you go close to maturity, or there's no more volatility, and therefore you know it's out of the money and you don't need to buy any underlying asset to replicate the option. And of course, then you have this knife edge case where the price of the underlying is exactly equal to the discounted strike price. Well, that's where just a small change in the underlying asset up or down, you switch between 1 and 0 positions to replicate the option, and therefore delta is just going to be 0.5. We can also graphically look at an example where we have a strike price of an option of $75, volatility of 30%, interest rate of 5%. And now what we're going to do is we're going to change that time to maturity. We start with 1.5 years. That will show us what the delta looks like depending on the underlying asset price. So we know if the underlying asset price is very small, then we know the delta is going to be 0 because you're very deep out of the money. If the underlying asset price is very high, then we know delta is going to be very close, or it's going to be 1 because we are very deep in the money. As we change now that time to maturity from 1.5 year to 1 year or half a year, or basically just shortly before maturity, this line becomes more and more extreme to eventually you just flip between 0 and 1 for delta. And exactly here on that point where you're at the money, that's where the delta is going to be just 0.5. So if you think about an entire portfolio and would like to figure out what is the change in your entire portfolio P, if the price of an underlying S changes by a little bit, well, then we can construct this delta of the entire portfolio. And let's denote the value of each position in our portfolio by Vj for the position in asset J, and the delta of asset J is just how much the value changes of that asset with respect to the change in the underlying asset. If you now consider a portfolio with value P, where this value P is just given by the weighted sum of all the values of these assets in the portfolio, now we can write the delta of the portfolio by how much the portfolio value changes as S changes a little bit, well, simply by plugging in for the portfolio price this weighted sum of values of all the assets and taking the derivative of this thing. And of course, that means we just have now this weighted sum over all these first derivatives, which is the same as just taking this weighted sum of all the deltas of all these assets in the portfolio. And that gives you this risk exposure of this entire portfolio to change in the underlying assets. So what is this useful for? Well, basically, if you would like to have no exposure to small changes in that underlying asset price S, then what you would like to do is you want to construct your portfolio such that the delta of the entire portfolio is going to be exactly 0. In that sense, you know that if the price of the underlying asset changes a little bit, your portfolio value will not change. And so you're perfectly hedged against these risks. The next thing I want to look at is the theta of an option. And theta is defined as the sensitivity of an option price as time changes a little bit. So what you do is you take the partial derivative of your option price. Again, the option price is a function of price of underlying, of volatility, interest rate, and time to maturity. And so in that time to maturity, you see that if you change time a little bit, basically your time to maturity changes, and so your option price is going to be affected. Notice that if I proceed forward in time, that means basically time to maturity shortens, and so I can rewrite this derivative as minus the partial derivative of how the option price changes as the time to maturity changes. Because that minus sign just comes from, because again, time to maturity shrinks as you proceed forward through time. So what does this mean? It basically says that, look, even if the price of the underlying asset doesn't change, even if volatility, so risk doesn't change and interest rates doesn't change, then your option price is still going to change because you get closer to maturity. And this, of course, is just because the time value of that option is going to be affected. If the time value of an option is positive initially, then if you get closer to maturity, well, then it means your option loses value. If time value of the option is actually negative, then getting closer to maturity means that your option price actually gains in value. Now for a call option, we know that the time value of the call option is always positive, at least if there's no big dividend payments, and therefore the call option always loses money as you get closer to maturity. And we also call this that the call option bleeds through time if nothing else happens. For a put option, it's going to depend on how deep you are in the money, whether the time value is positive or negative. If it is positive, then again we can say that the put option bleeds as you get closer to maturity because it loses value. And the last bullet point, I'm going to mention this again when we talk about the gamma of an option, but basically options, if they have a positive time value and if you hold them and nothing happens, then basically we call it the cost of holding an option or taking a long position in gamma. But again, we see afterwards what it means, a long position in gamma. In the Black-Scholes formula, if we take the partial derivative with respect to time, then theta for a call option is given by this formula over here. Now there's a nice interpretation. The second term over here we take the derivative with respect to time, and what happens is it's going to affect this discounting of the strike price. If you get closer and closer to maturity, there is less discounting of the strike price, so we have minus this term over here. And so the interpretation again is if you get closer to maturity, the time value of money works against you, because if you exercise that call option, then you actually have to pay that strike price actually sooner. So if you get closer and closer to maturity, there's less discount of that strike price. That's bad for you. The first term captures actually the cherry picking right, and that first term comes from taking the derivative with respect to these probabilities of ending up in the money. And what does this mean? Well, for a call option, if you have time left to maturity and you can wait and see whether the price of the underlying is going to be high or low, and then decide whether you want to exercise the option or not, that actually gives you some value. It is this cherry picking right. And if you get closer and closer to maturity, well, then you have less time to decide whether you actually want to buy the underlying or not. And so this cherry picking right is deteriorating. So overall, for a call option, you see that the theta is going to be negative, both because of the time value of money and the cherry picking right, which both affect you negatively as you get closer to maturity. For a put option now, we see a slightly different equation. So the first term over here, that captures exactly the same effect of that cherry picking right as for the call option. Indeed, these two terms are exactly the same. And that's because, again, for a put option, you also would like to wait and see what happens to the underlying asset. If it actually drops a lot, then I want to exercise, otherwise I don't. And so that cherry picking right is valuable, and the longer I can wait, the better this is. And so if you get closer to maturity, that cherry picking right decreases, which is bad for my option. Now, in contrast to the call option, the second term is actually positive. And why is that? Well, we said that with a put option, if you exercise it, you actually receive the strike price at maturity. But now for the put option, you have to discount that strike price, which is actually bad for you. So having a lot of discounting has a negative effect on your put option. And so getting closer to maturity, there will be less discounting of the strike price, and that's going to affect you now positively. So that's an offsetting effect. Eventually, whether the second or the first term is larger in magnitude, that's going to determine whether your time value is actually positive or negative. So if the second term is larger than the first term in magnitude, then your time value is negative, and then getting closer to maturity is actually good for you, and theta is positive. If the second term is smaller in magnitude than the first term, then your time value of that put option is positive, and getting closer to maturity is bad news for you, because the put loses now money as you get closer to maturity. Notice just one thing about these derivatives. The small phi over here, that's the first derivative of that large phi. Remember that large phi, that's that integral where you sum up all this probability of the standard normally distributed variable being between minus infinity and d2 in this case. the small phi, that's exactly this probability for some value d1 of that normal distribution, or this distribution density function. So we already talked about that. For a call option, theta is always negative because the time value is positive for the call option and it loses, or the time value shrinks as you get closer to maturity. For a put option, it can actually also be positive if the put option is very deep in the money and the time value is negative. So then the put option increases in value as you get closer to maturity. Again, these two bullet points just explain again that the first term is about the cherry picking right, while the second term is about the time value of money, or this discounting of that strike price. Tata hatching is basically the same idea as delta hatching. If you look at an entire portfolio and you want to figure out how much does the portfolio value changes as you move a little bit through time and nothing else changes, well, then we want to take the derivative of your entire portfolio value with respect to time t. And again, if you think about, you have a portfolio which consists of many different assets, and W are these investments, these weights, and how much you invest in these assets, then the theta of your portfolio is just going to be the weighted sum over all the thetas of these assets in your portfolio. So again, if you would like to have a portfolio which doesn't change in value as you move through time and nothing else changes, then we can combine our positions which you have in our portfolio with some derivatives such that the overall theta of the portfolio will be zero, and then we don't gain or lose money anymore as we move through time. Next thing is going to be the gamma of an option, and the gamma of an option measures by how much does the delta of the option change as the price of the underlying changes a little bit. Or in other words, it's the second derivative of the option price with respect to the price of that underlying asset. If you write the put-call parity, and remember the put in the put-call parity can be written as a call option and short selling an underlying asset, dealing with dividends, and then also lending some money. Now, if you take the second derivative of the put-call parity with respect to S, well, then you have on the left-hand side the put, taking second derivative of it, that's just the gamma of the put. Then on the right-hand side, you have the call option, taking second derivative, that's the gamma of the call. And then short selling the underlying asset, so you have minus S, taking the second derivative of it, that's actually zero. Plus then any of the positions in risk-free assets, well, they don't change as the price of the underlying asset changes, and so they don't have any gamma either. So from the put-call parity, then you see that the gamma of a put option has to be exactly the same as the gamma of a call option. And this is an important thing, or a useful thing to remember, that the gamma of put and call options are exactly the same. Delta changes exactly by the same amount as the underlying asset changes a little bit for both put and call options. Now, how do we interpret a gamma, let's say, of 0.06? This means that if the underlying price changes by $1, then a trader who tries to replicate the call option by buying delta numbers of the underlying, or a put option by short selling some units in the underlying, has to adjust his hedge by exactly 0.06 numbers of the underlying asset. So if the underlying asset increases by $1, then the delta has to be adjusted by 0.06, or meaning you have to buy 0.06 additional units of the underlying asset to hedge a call option. The gamma really measures this curvature or the non-linearity of an option, and therefore it is really this essence of the optionality or the cherry picking right. And that thing is going to be the largest if you are somewhere close to the at the money of an option. So that was an argument which you have seen in earlier chapters, where we said that, well, if you're very close to at the money point, then the uncertainty is the biggest whether you want to exercise your option or not, and therefore being able to wait and see what's going to happen that value is going to be the largest, or this cherry picking right is going to be the largest. And that's going to be reflected in the gamma being very large if you're close to at the money. Now, taking a long position in gamma, that basically means buying an option. Let's, for example, say taking a long position in a call and short selling these delta numbers of stocks and B numbers of bonds. What does the gamma look like in the Black-Scholes formula? So if you take the second derivative of the Black-Scholes formula with respect to S for either a call or a put option, you're going to get exactly the same. And again, this thing is always going to be positive. We have seen before this red curved line, that's the price of a call option. The delta was measured by the slope of that red line at some point. So for example, if the underlying asset price is $70, then the delta is 0.42. Now, if the price of the underlying increases a little bit, then you notice that because the red line is curved, the slope is going to change from first that black line, which was 0.42, it's becoming steeper, and the gamma will tell you now the slope is going to increase by 0.05, so from this 0.42 to 0.47. If you go back to this long position in gamma, if you buy a call option and you short sell delta stocks and B number of bonds, what does this mean? So let's consider you are at this point over here where that price of the underlying is about $70. So buying the call option, having this value of the call option right here around $10 or so, and short selling that replicating portfolio, which also costs $10. Now, if the price of the underlying changes, let's suppose it increases. Well, if it just changes a little bit, we know that because the slope of the red line is exactly the slope of that black linear line, which is this replicating portfolio, then all the gains in the call option gonna exactly cancel out with the losses which I have from short selling that replicating portfolio of delta numbers of stocks and B numbers of bonds, again captured by this linear black line. However, if the price of the underlying increases a lot, let's say to $100, now the price of the call option increases actually quite a bit, while the value of that replicating portfolio of delta numbers of stocks and P numbers of bonds only increases from $10 to a smaller value of, let's say that's about 20 something dollars, while the call option is in like its mid $30. So that difference then is a gain which I make because, well, my call price increased more than this replicating portfolio which I short sell. So if the price of the underlying increases a lot, I actually make a gain by having that call price and short selling that replicating portfolio. Now, what happens if the price of the underlying drops quite a bit? Let's say it drops here to $50. Then the price of the call option is going to be still somewhat positive, so $2-3, and the price of the replicating portfolio here is basically around zero. So what does this mean? Well, basically again, owning the call option and being short that replicating portfolio, that gives me actually again a gain. So I make again money. So what does this mean now? So this portfolio of buying one call option and short selling this replicating portfolio, or what we call taking a long position in gamma, this makes money whenever the price of the underlying increases a lot or decreases a lot. And so basically it says we never lose money. Well, so that's actually a nice thing. However, one thing which we have to consider is, what if the prices don't move at all? What if the underlying asset price just stays exactly the same over maybe a day or 2 or 3? Well, then one thing which we have to consider is that the price of the call option becomes smaller and smaller. That's what we call the call option is bleeding, and that red line becomes closer and closer to that intrinsic value of that blue line. Okay, so you have basically a downward shift of the red line and becoming closer and closer to the blue intrinsic value line. So that means that if the price of the underlying doesn't change at all, Now my call option decreases in value, but my replicating portfolio of delta numbers of stocks and B numbers of bonds remains the same. So basically having the long position in the gamma will lose money if the price of the underlying doesn't move much or if it stays even constant. However, you do make money if the price of the underlying changes sufficiently, whether it increases or drops. And I'm also going to illustrate this over here. So that tells me how much does the price of the underlying asset change, whether it increases a lot or it decreases a lot. And that curved line over here, that's this long position in gamma that says buying one call option, which I write here by FT instead of what I had over here, the CT. And then short selling the replicating portfolio, so having minus delta numbers of stocks and minus this pi, where the pi thing is the B numbers of bonds times the bond price. Okay, so it says that, well, if nothing happens, if the price of the underlying doesn't change, well, then my call price loses money because it becomes closer and closer to intrinsic value, while the replicating portfolio didn't change its value, so that means I make a loss. But if the price of the underlying increases a lot or decreases a lot, then I make money by buying the call option and short selling that replicating portfolio. So in that sense, having a long position in gamma or buying the call option and short selling this replicating portfolio, that is a speculation that the price of the underlying changes sufficiently much. On the other side, taking a short position in gamma, which would mean buying that replicating portfolio and short selling the call option, that's the opposite speculation. So here you actually hope that the price of the underlying doesn't move much, that basically nothing happens in the market, and you're just going to benefit from the call slowly bleeding out. Of course, you can also do the same thing with a put option instead of a call option. So you buy the put option and you short sell the replicating portfolio. So that would be the equivalent thing, since the put option has the same gamma as the call option. We can also look at limiting properties. So what happens if you are very deep in the money? So this from the perspective of a call option. If you are very deep in the money or very deep out of the money, well, then gamma is just 0. And why was that? Well, let's go back to this picture over here. If you're very deep in the money, then we know delta is exactly equal to 1. And if the price of the underlying changes a little bit, that slope is not going to change. So if you're already very deep in the money, if the price increases further or just drops a little bit, you still know you're going to exercise that option at maturity and your delta is going to stay 1. Nothing changes. Similar if you're very deep out of the money, and if whether the price of the underlying increases or decreases a little bit, you still know this option is going to be worthless. You still know it's not going to be exercised in the future, and therefore delta doesn't change, and therefore gamma is going to be 0. The most interesting thing for gamma is if you're close to at the money, and in particular if you get very close to maturity or if volatility becomes very small, then your gamma is becoming very, very large. And I'm going to illustrate that also with this figure over here. This is for an option with strike price of $75, 30% volatility, then interest rate of 5%. And now we look at different times to maturity. We start with 1.5 years. That's illustrated by this red line over here. So it shows us that depending on how high the price of the underlying asset is, how big is this gamma. If you get closer and closer to maturity, then your gamma is going to increase. Eventually, if you're very close to maturity, your gamma is going to be very large if you are close to at the money, and otherwise it's just going to be 0. Gamma hatching. So again, it's the same argument as we had before. If you think about the portfolio where you have some assets with values V, J, and you invest in these assets, and the portfolio weights are given by this WJ, so how much you invest in each asset, then the gamma of your portfolio is just going to be, well, you take your portfolio value, take second derivative with respect to S, and that's just going to turn out as this weighted sum over all the gammas of your assets in the portfolio. So if you would like to hatch a gamma in your portfolio, what you want to do is you want to buy or sell certain derivatives such that the overall gamma of your portfolio is going to be close to zero. And therefore, you can be sure that you don't have to readjust your delta. You basically hedge away not just small changes in the underlying asset, but also larger changes in the underlying asset. Just maybe one point to notice here, you can only use options or some derivatives which are non-linear in their dependence on the underlying asset to actually change the gamma of a portfolio. So just buying the underlying asset itself, well, because buying the underlying asset, the price is just S, and taking the second derivative of that is zero, that doesn't actually help us to change the gamma of a portfolio. And similar investments in risk-free assets like buying or selling bonds, they don't have gamma, so they cannot be used to hedge that risk. The option Vega is measuring how much the option price changes as the volatility of the underlying asset changes a little bit. And again, if you would look at the put-call parity, where the put is equal to the call price minus the price of the underlying asset, dealing with dividends and lending some money, then if you take the derivative with respect to sigma, well, underlying asset actually keeping S constant, the underlying asset doesn't change as I change sigma a little bit, the risk-free asset doesn't change as I change sigma, and so therefore you see again that put and call option both have exactly the same Vega. They change the same as the volatility changes a little bit. If you think about Vega, it captures by how much the price of that option changes as your risk changes. And you might be tempted to say, well, this is basically the same as gamma. It captures this non-linearity, but it's not quite true. So gamma and Vega are conceptually a little bit different. And just to illustrate that, how is Vega different from gamma? I have two examples here. One would be a forward written on an option. So basically meaning you lock in the price at which you buy an option at some future date. That forward of an option doesn't actually have any gamma, but it has Vega. Why is that? Well, because if the volatility changes, then the option price is going to change, and so that's going to affect this forward option. On the other side, if you look at Vega, it actually increases with the time to maturity. The more time you have left to maturity, the overall volatility of that underlying asset is larger, and therefore the option value is higher or more sensitive to changes in volatility. But on the other side, gamma is actually smaller as you're more far away from maturity. So gamma and Vega are quite different if you change the time to maturity of a derivative contract. Calendar spreads are interesting because we use options with different times to maturity, and there we can actually play around gamma versus Vega. So by using a call option with a longer and a shorter time to maturity and combining them together, what we can actually do is we can have zero Vega and only exposure to gamma. Or on the other side, we could construct a combination to get a zero gamma but getting some exposure to Vega risk. These calendar spreads, although the payoff looked very similar to a butterfly spread, as we have seen in the earlier chapter, here it becomes more interesting where you want to construct strategies where you only want to have exposure to either Vega or either gamma risk. In the Black-Scholes formula, Vega, again, you take just your Black-Scholes formula and take the derivative with respect to volatility. It's always going to be positive. So if volatility increases, well, then actually the cherry picking right becomes more valuable, and therefore the Vega is positive. So both call and put option become more valuable as risk increases. Now notice that in the Black-Scholes formula, sigma, or this volatility, is actually assumed to be constant. So in that sense, it's a little bit weird to look at Vega because it's actually going against the assumption of the Black-Scholes formula. Nevertheless, in practice, we know that volatility is changing through time, and we're going to talk later about how to adjust the Black-Scholes formula to capture that or take that into account. So traders will still be interested in hatching these changes in risk. Let's look at some pictures over here. So what we start with is again an option with a strike price of $75, 1.5 years to maturity, and the risk-free rate is equal to 5%. And then we draw a couple of different options illustrated by all these different curved lines. The most extreme is the intrinsic value. That's basically where volatility is 0. Nothing happens anymore. And then as we increase volatility, this line shifts more and more towards this upper left corner away from the intrinsic value. So what does it mean? It basically means that the cherry picking right, or this time value of the option, is increasing as we have more risk. And you can get the same thing for a put option. Again, here we know that if you're very deep in the money, well then we know we exercise that put option for sure, and we don't actually care about the cherry picking right anymore. But if you're somewhere closer to at the money, then if we increase volatility, then we would like to wait and see what's going to happen in that underlying asset before we make the decision whether we exercise or not. So that cherry picking right increases and increases more and more. So here we want to look at how Vega depends on the price of the underlying asset. And what we see is that if you are in the tails, either on the very left or on the right-hand side, where the price of the underlying asset is very low or very high, that's when Vega is 0. And if you're very close to at the money, then Vega is very large. Now, what is the reason for that? So let's consider a call option. If the price of the underlying is very low, that means the call is very deep out of the money. And therefore, even if risk becomes larger, if you're very, very deep out of the money, then increase of risk still not going to matter that much for your cherry picking right, because again, you're still pretty much certain that the option is going to be out of the money. So that means that basically Vega doesn't matter, or this increase in the risk doesn't matter. Similar, if you're very deep in the money, then a change in the risk is not going to affect you a whole lot, because anyway you know that you're going to exercise that option, and therefore you basically just know you buy that underlying asset, and now a change in risk is not actually going to affect by how much that is worth. The most interesting thing is if you are close to at the money. If you increase risk now, then again this cherry picking right increases a lot in value. So here I really want to see now whether I'm going to end up in the money or out of the money. So I want to wait and make this decision later, and that's why an additional increase in risk is going to make that cherry picking right even more important, and Vega is going to be very high. How do you hatch Vega? So again, if you look at an entire portfolio and think about how does this portfolio value change as the sigma of an underlying asset changes a little bit, well, rewriting the portfolio price again as this weighted sum of the values of all the assets and taking derivative with respect to sigma, that tells us, well, portfolio Vega is just the weighted sum over all the Vegas of the individual assets in your portfolio. So if you want to hedge risk with respect to changes in volatility, well then what you want to do is you want to make sure that your portfolio Vega is close to 0, and so you have to add additional options, long or short positions, to make sure that this weighted sum over all these Vegas is going to be close to 0. Lastly, we will look at rho. Rho is the change in the value of a derivative if the interest rate changes a little bit. And under the Black-Scholes assumption, so if you look at the call option, then rho is actually always going to be positive. What does it mean? Well, if interest rate increases a little bit, because for the call option I only have paid at strike price at the maturity, and looking at the present value of paying that strike price, if interest rate increases, that means I have to effectively pay less in terms of present value of that strike price. And therefore, an increase in the interest rate is going to increase my call option value. The rho of a put option is negative, so it's exactly the opposite of the call option. And that's because, again, if I have a put option, if I exercise it, I will receive the strike price. But again, I only receive that at the maturity date. So if I'm at some date before maturity, discounting the strike price is actually decreasing the value of my option. So if the interest rate increases, I discount the strike price more. That's going to be bad for me. That's going to decrease the value of my put option. How do you hedge rho? Well, that's essentially a duration-based hedge. So what you do is you take the derivative of all the assets in your portfolio with respect to the interest rate R, and so that's just going to give you the weighted sum over all these rows. That's the rho of the entire portfolio. Again, what is that? Basically, that's the duration of each asset, and we know that the weighted sum over all the durations, that's the duration of a portfolio. If you want to hedge yourself against small changes in interest rate risks, and what you want to do is you want to have the duration or that rho of your portfolio to be very close to zero. So finally, putting everything together, if you're a trader and you want to hedge risks, then you say that, well, if I look at the change in my portfolio value from some TI to TI plus 1, then how can I approximately write that? Well, the portfolio value changes because I move through time. And even if nothing else happens, even if the price of the underlying doesn't change, volatility doesn't change, interest rates doesn't change, that portfolio price may still change. And how much does it change? Well, it changes according to the theta of my portfolio. And then in addition to that, if the price of the underlying changes, S, well, then I need to consider how big is the delta of my portfolio. And then I can consider by how much the volatility changes of that underlying asset and multiply that by the vega of my portfolio. And we also have changes in interest rate, and I have to multiply these changes in interest rate by the rho of my portfolio. And eventually, because I know that prices on the underlying changes may be quite large, I basically do the second order approximation where I do 1/2 the second derivative of my portfolio price change with respect to the underlying price change, and this thing is nothing else but the gamma of my portfolio. In that sense, using this Taylor approximation of the change in the portfolio price with respect to time and all these risk sources of either the change in the underlying asset or even if it's a large change, and also with respect to change in volatility and interest rates, that can all be written using these Greek letters. And so here's this funny joke. Basically, what does a trader have to do to get rid of as much risk as possible? Basically, he has to carefully manage all the Greeks. Why is this funny? Well, it's funny in light of the recent financial crisis. After 2008 and 9, basically Greece was in big trouble. And we were all worried that Greece is going to default and it had to be bailed out by the European Union, especially by French and German taxpayers. And so basically in this crisis, everyone also was saying we do have to manage the Greeks to get rid of all the risk. Now, the last thing I want to do is I want to look at a numerical example. Let's suppose you have a portfolio with a delta of 0 and a gamma of -5,000 and a vega of -8,000. Let's suppose now you have an option with a delta of 0.6, a gamma of 0.5 and a vega of 2, and another option which has a delta of 0.5, gamma of 0.8 and vega of 1.2. Now all the Greek letters which I have given here, delta, gamma and vega, they are written with respect to some underlying stock S. If you want, you could think of this maybe as the SPDR ETF, so the ETF written on the S&P 500. Now, what is actually the delta, the gamma, and the vega of the underlying asset itself? Well, the underlying asset price S is just equal to a 45-degree line in this payoff diagram. If you think about how much is S worth if S has a certain value, well, it's just equal to S. So what does this mean for delta? Taking the derivative of S with respect to S, well, that means delta is just equal to 1. Now, what is the second derivative? Well, the derivative of number 1 with respect to S, that's just equal to 0, and therefore gamma is equal to 0. Moreover, how much does S, the price of the underlying, change if sigma changes a little bit, keeping everything else constant, so meaning also keeping S constant? Well, then by definition, keeping S constant, then S doesn't change, and therefore Vega is 0. Whenever we write our Greek letters, we always said that, well, we look at some option or some derivative or some asset as some function of S, sigma, the interest rate R, and time to maturity. And if you think of what is this function for just the underlying asset itself, well, it is just the variable S. Okay, so again, taking the first derivative with respect to S of this thing, that's just 1. Taking the second derivative, that's 0. Taking the derivative with respect to sigma, that is 0 as well. My question is going to be, what position in option 1 and the underlying asset S do I actually have to take to combine that with my original portfolio, which had that delta of 0, gamma of minus 5,000, Vega of minus 8,000, such that it is delta and gamma neutral. What does it mean, delta and gamma neutral? That means I want of my new portfolio, so combining my old portfolio with new positions in option 1 and that underlying asset, I want this new portfolio then to have a 0 delta and a 0 gamma. How do you do that? I have a gamma of minus 5,000. Adding any stocks to that portfolio will not change that gamma because gamma is 0 of the stocks. Adding options of type 1 to that portfolio, that will affect the gamma. How many option 1s do I have to buy to offset these minus 5,000 gamma? Well, it's going to be exactly 10,000 options of option number 1. Okay, 10,000 times 0.5, that's going to give me plus 5,000 gamma. Okay, so the first thing I do is I say, well, to that portfolio which I already have, I add 10,000 long positions of option number 1 to make sure that the gamma is 0. If I add 10,000 long positions of option 1 to my portfolio, then I actually also change my delta. Initially my delta was 0. Now I add this 10,000 times 0.6. That means I increase the delta to 6,000. How can I make my delta equal to 0 and not affect gamma? Well, I can actually combine that now with some positions in my underlying asset S. And so how do I do that? I have 6,000 delta, and I know my underlying asset has a delta of 1. Therefore, I want to short sell 6,000 numbers of that asset S. That will then introduce minus 6,000 delta to my new portfolio, which offsets exactly the 6,000 delta which I get by adding that 10,000 units of option number 1 to my portfolio. What positions do I need to take in option number 1 and my underlying asset S if I want to make the new portfolio delta and Vega neutral? So going back over here, we do basically the same thing. We said our current portfolio has a Vega of minus 8,000. Adding stocks to that will not affect the Vega, but adding options to that portfolio, that will actually change my Vega. And how many options do I need to add to the portfolio? Well, if I add 4,000 options, 4,000 times 2 gives me a change in Vega by 8,000. That offsets my current negative Vega of minus 8,000. Now, if I do buy these 4,000 options, then my delta changes to 4,000 times 0.6, which is 2,400 delta. And so to offset that, I want to now short sell 2,400 units of the stock So now that overall portfolio, the old portfolio plus adding 4,000 options of type number 1 and short selling 2,400 units of the stock, that will make sure that both delta and vega will be equal to 0. The last question asks, what positions in option type number 1, 2 and the underlying assets will I have to add to my original portfolio to make the new portfolio delta, gamma and vega neutral, so setting all of these equal to 0. So the way I'm going to do this is I set up a system with 3 equations with 3 unknowns. The unknowns are the weights on option number 1, 2 and the underlying asset. And the equations are going to correspond to what is my position going to be in delta, gamma and vega of that new portfolio. So the first equation which we see over here that says, look, my current portfolio has a gamma of minus 5,000. Now I add to that W1 numbers of option 1, where each of those option 1 has a gamma of 0.5. And then plus W2 that measures how many options of type 2 I add to my portfolio, and each of that has a gamma of 0.8. And the last term is 0 times W3, where W3 captures how many units of the underlying asset I add to the portfolio, and each of them actually has a gamma of 0. So that's not going to affect my gamma. Then the second equation over here is for the vega. I say my initial portfolio has a vega of minus 8,000. Again, I add W1 numbers of option number 1 to the portfolio, and each of those options has a vega of 2. And similar, I add W2 numbers of option 2 to my portfolio, and each of these options has a vega of 1.2. And finally, again, I have W3 numbers of the underlying asset, and again, the underlying asset has a vega of 0, so this is not going to affect this equation. And the final equation is going to be the delta of my current portfolio here is actually 0. Then I add the W1 numbers of option 1 to my portfolio. Each of that option has a delta of 0.6. W2 numbers of option 2, where each of them has a delta of 0.5. And now I also add W3 numbers of stocks to my portfolio, and each of them has a delta equal to 1. Now, all of these gamma, vega, and delta of the new form portfolio, they all shall be equal to 0. That means to make my portfolio delta, gamma, and vega neutral. Now, so I have these 3 equations in these 3 unknowns, so I can solve for W1, W2, and W3. And it turns out that what you should do is take 400 long positions in option type number 1, 6,000 long positions in option type number 2, and short sell 3,240 units of the underlying asset together with my old portfolio. That will make sure I have delta, gamma, and vega of the new portfolio is exactly equal to 0. In practice, traders are concerned with various types of risks. Typically, traders try to be delta neutral at least at some point during the day. And then when opportunity arises, they will actually also try to make themselves gamma, vega, rho, and theta neutral. But typically these other Greek letters are less of an importance to traders than delta. Because delta is kind of the first order effect because S moves around all the time, or the price of the underlying asset. Finally, I would like to give you an interesting example of what happened in October 1987, where portfolio managers were hedging risks, but then eventually caused a crash in the stock market. So basically, what happened in the 80s is that a lot of portfolio managers bought put options to hedge their downside risks or protect themselves against a crash in the market. And what happens is that people who sold the put options to these portfolio managers, they in turn wanted to hedge themselves, and the way they did it is by doing these delta hedging, meaning that they actually had to short sell some of the market, since again delta of the put option is between -1 and 0. What happened is in October 1987, the market started to decrease, and in turn, all these traders who were delta hatching, who were selling these put options to the portfolio managers, they started to short sell more of the market to keep their delta hedge as good as possible and make sure that they don't have risk exposure. And so what happens as these guys are short selling the market is that, well, market prices drop even more. And this resulted in a downward spiral where they had to short sell even more to hedge their put options, which they were selling to portfolio managers. And therefore, again, they had to short sell more and price in the market dropped more. And again, they had to short sell more and so forth, eventually leading to a very big crash within just a very short time span.